Dr. Josh Dillon. He received his PhD in physics in 2015 from MIT, working with Professor Max Tegmark.
I wish.
Amazing how that comes out. Yeah. A bit younger. Okay. He's now an NSF, Astronomy and Astrophysics postdoctoral fellow at UC Berkeley, working with Professor Aaron Parsons on the hydrogen Epoch of reionizing array HERA project. His research focuses on the theory and practice of data analysis for 21 centimeter cosmology, a new way to map neutral hydrogen throughout cosmic time with low frequency radio telescopes. Josh grew outside Chicago, got his BS in physics from Stanford University, and likes being in California. The last century has seen a revolution in our understanding of the universe and our place in it. We now know that the universe is about 13.8 billion years old and is only about 5% of normal matter. Uncovering the nature of the other 95%, the mysterious dark matter, and even more mysterious dark energy, is one of the most important questions in fundamental physics today. Dr. Dillon will talk about a new technique being developed at UC Berkeley with collaborators around the world using radio telescopes to make huge 3D maps of hydrogen, the most abundant element in the universe, to test our cosmological theories. He will explain the observational challenges being faced and why we're building a giant array in the middle of the South African desert. He'll discuss how we know what we know about cosmology today and how we can use the discoveries from the radio telescopes. Join me in welcoming Josh Dillon.
Thank you so much for the invitation. Can the people in the back hear me okay without the microphone? Yeah. Okay, everyone is happy. So before I get started, please feel free to ask questions. I'm here to explain these ideas, and if I'm going too fast, if something's confusing, just go ahead and ask. I'm trying to give this talk at a level where people who don't necessarily have a technical or mathematical background can still understand and appreciate the kind of science that we're working on. So I'm going to start by going back about 100 years to the beginning of modern cosmology, which began with this guy, and most of you are probably staring at Einstein. No, actually, I mean that guy in the background there. You may not recognize his face, but you definitely recognize his name. That's Edwin Hubble, and he's quite famous for a few different discoveries. So, in Hubble's time, this is what we thought the universe looked like. We now know that this is the Milky Way galaxy, but at the time, people thought that was the universe. That was everything there was, and we were able to measure distances to stuff in the Milky Way galaxy, and we kind of had a sense of roughly how big the universe was, which was, tens of thousands of light years, which is big, but not as big as we know it is today. So what was discovered around that time was this really interesting idea that there's a particular kind of star, and if you measure it, you could actually know, if you measure how bright it is, you could know how far away it was because it had a very standard brightness. So the way to think about that is that the further away it is, the dimmer it is. And the closer it is, the brighter it is. And it's much easier to measure how bright something is than how far away it is in astronomy. So these things were what were called standard candles. You could standardize them in the sense that you could see, based on how bright they were, how far away they are. Because we know how light goes as you get further away from something. We know mathematically how much dimmer it gets. And what he did is he started looking at these fuzzy things that were called spiral nebulae at the time. And now we know that they're not spiral, they're not nebulae, they're galaxies themselves. And what he found was that they were further away than the whole universe, which of course doesn't make sense. What he found is that they're outside of the universe, they're really, as we now know, outside of the Milky Way. So that was one of Hubble's main discoveries, is that there are things outside of what people thought was the universe. And it was a major discovery in the sense of expanding our knowledge. But he didn't stop there. So he also looked at the spectrum of light. So you basically pass the light through a prism and you look at the various spectral lines. Maybe many of you have done this with light from the sun, where you pass it through a prism and you can see these lines. And what he found was that all of the lines that you normally associate with various elements, hydrogen and iron and stuff that we know is in stars, those lines were all redder than they should have been. They were redder because, just like a Doppler shift, where something that's going away from you sounds like it's at a lower frequency, something that's moving away from you has redder light. Now you have to be moving very fast to actually have sort of a perceptible extra bit of redness, or what we call redshift in astronomy. But these things were moving away. And in fact, almost all of the galaxies, we now know that these are other galaxies, not part of our Milky Way galaxy, were moving away from us. So Hubble is also famous for this particular discovery. I think this is the only real graph I'm going to show you. This is from a paper from the 1920s. And basically what he found is that the further away, parsecs are a unit of distance, the faster things were moving away from us. And that's kind of puzzling, because it seems like, well, one explanation, if things are moving away faster, the further you go, we're in a very special place where things are slow moving here, and the further away you get from our special place in the universe, things are moving faster. That's one explanation, but that's not a very good explanation. A better way to think about it is that if velocity is proportional to distance, higher velocity, higher distance, the whole universe is expanding away from itself. From the whole universe is expanding, period. So wherever you are, it looks like everything is expanding away from you because everything is expanding away from everything. And that was actually a prediction that Einstein could have made and famously did not. You saw in his general theory of relativity that the universe could expand or contract, that space itself could change size, and that was totally fine. And he said, no, that's ridiculous. And he put in an extra constant to get rid of that effect. But Edwin Hubble took a more empirical approach, and he said, well, it does sound ridiculous, but it's the only way to explain what we're seeing, and that was the discovery that the universe was expanding, which is a pretty major discovery. So one interesting thing about that is that if you are looking at objects that are redder and further away, you're also, because astronomy is kind of like a time machine, the further away something is, the longer it's taken to get to us. So we can go all the way back to the reddest things that we can observe in some sense. We're looking all the way back to the beginning of the universe, to the Big Bang. That's the highest, most redshifted things we can observe. And in particular, the sort of earliest thing we can possibly observe, many of you have probably heard, actually before I talk about that, sorry. So one thing we can do is we can make maps of galaxies in the sort of relatively nearby universe. So we can look at the redshift of galaxies, and we can say, okay, if we know how the universe is expanding, we measure their light, their frequency, we get this redshift that tells us where that galaxy is. We can make these huge 3D maps, and there's all kinds of really interesting structure on very large scales, where we're seeing like these sort of what's often called the cosmic web. And that's a structure that's grown from basically galaxies collapsing under gravity. And this is a really cool movie from the Sloan Digital Sky Survey, which I've always liked. So this is what we can see if we're looking at galaxies, just looking at their redness. On the other side, we can also look back all the way to the closest that we can see to the Big Bang, at least directly with light, and that's the cosmic microwave background. So that's light, the afterglow from the Big Bang, that was emitted 380,000 years after the Big Bang, when the universe cooled enough that it could be emitted and transmitted through the gaps between galaxies. And then that light has now come to us, and it's redshifted by a significant factor. So this is what that cosmic microwave background looks like in the Planck satellite that took this famous picture of it. And it's actually, you probably heard lectures before about previous generations of satellites measuring this out. So we can learn a lot from the cosmic microwave background. So for example, what we're seeing is what the universe looked like when it was 1 billion times denser on average. And that's because the universe has expanded by a factor of 1,000, roughly, since this light was emitted. So all of this light itself has expanded just because of this redshifting. As the universe expands, the light itself expands, and so we're seeing it at a wavelength that's 1,000 times longer than the wavelength when it was emitted. And it's now just finally coming to us after 13.8 billion years of travel. And this is the time in the universe when it had just gone from being a plasma, which is when protons and electrons are just this sort of free-flowing gas, to when we be able to make hydrogen and helium atoms, so when atoms are combining. And that's that epoch of the universe that we're seeing. This is sometimes called recombination, though it should be called combination. And that's the time when the protons and electrons found each other, and they went from being a plasma to being a gas. As the universe was expanding, it was also cooling. As I said, it was 1,000 times hotter when this was first emitted. But one thing that this map doesn't generally show you is that this density contrast is kind of fake. what's really going on is that you're seeing places that are slightly hotter or slightly colder at the 0.001% level. That's one reason why this was a very hard experiment to do and why George Smoot and others won the Nobel Prize for this. But the idea is that you're looking for this very, very faint fluctuations. And that's because when the universe was 1,000 times smaller, it was also much more homogeneous. The universe really had a uniform density and temperature, and it didn't change very much from place to place. Whereas today, obviously, that's not true. So there's a question then. We went from a time when the universe was extremely homogeneous to a time when the universe was really not homogeneous at all. We have life on Earth, for example, is very different from out in the middle of the gas between galaxies in terms of temperatures and densities and number of people and that kind of thing. So the universe went from being very boring in some sense, very much the same everywhere, to very complicated. So we've learned a lot from these two probes together, from looking at galaxies and from looking at the cosmic microwave background. As it was mentioned in the abstract, we've learned that the universe is only about 5% the stuff we're made of. So protons, neutrons, electrons, normal stuff. And it's about 27% dark matter, which is stuff we don't know what it is. And then the rest is apparently dark energy, which is stuff we really don't know what it is. But it's causing that expansion to accelerate, which was another thing that was definitely not predicted, but some people could have predicted it. It was a discovery that again led to another Nobel Prize. And maybe it's infinitely big. Seems consistent with that, though we can't prove that something's infinitely big, because that's not possible to prove. You can't go there and show that it's infinite. But the real question that we're interested in is this vast transition between 13.8 billion years ago and more or less today. And the question is, how did we go from being hot and dense and uniform, kind of the same everywhere, to complicated and cold and sparse and really hot in some places and very cold in others? And how do we have this basic transition? And of course, the answer is we don't really know because we haven't observed it directly. But we've got some theories. So this is a cartoon picture of what we think went on. So the sort of first interesting thing after the cosmic microwave background, the universe experienced this sort of long period of what we call the Dark Ages, where not much is going on except that things are starting to slowly collapse under their own gravity. But eventually that will lead to the first stars. And those first stars are probably quite different from the stars that we see today. They're probably a lot bigger, they probably died pretty quickly, and those led to the second generation of stars, and eventually the first black holes as well. And then those black holes started to have a pretty big impact. And then finally, after those first black holes and became part of those first galaxies, we have this period where we call the epoch of reionization, and then we finally get to modern galaxies. So this period in the middle here, where we go from first stars to the first black holes to the point where we have enough galaxies that they can start taking the universe, which I said had gone from being a plasma, the CMB, to being a regular gas, what we call atomic gas or hydrogen gas, where we think of it as a proton and electron together. And then eventually the gas between galaxies actually reionizes, so that's why we call it the epoch of reionization, because astronomers are not clever at naming things. And so and this is sort of another phase change in the universe. And we know this happened because we can observe the space between galaxies today, the sparse gas that's between galaxies, which again, we're uncreative, so we call that the intergalactic medium. And what we find is that that is pretty much completely ionized. So the universe went through another phase transition, probably driven by the first stars and galaxies. So poetically, and I think we got this one right, we call this whole thing the cosmic dawn, which I think is a pretty nice poetic term for what's going on, where it kind of sounds a little bit like a cult, but bear with me. So we have a lot of questions about this happened because this is really just a theory, and we need to actually go out and observe this and try to figure out what's going on. But we're talking about things that are extremely far away and extremely faint and very difficult to observe directly. And we have a lot of questions. So as I was wondering, where did the first stars come from? Another good question is what made these first black holes and what they looked like. So we think, for example, that the first black holes, let's see if I can get this go, were forming in these binary systems with other stars, so that they actually start accreting matter onto them, and then that will eventually create a lot of bright emission, X-rays and gamma rays and stuff like that are coming from this process. But we do know that these black holes exist and probably formed pretty early, And an amazing piece of evidence for that actually came out just a couple years ago. So here's a nice video. This is actually not real data, of course, but this is what sort of a simulation would look like of two black holes colliding. And so, for example, if you had one star and then another star who were orbiting each other, and they both went supernova and made black holes, eventually, many, many years later, basically the whole age of the universe later, occasionally those things collide. And it just so happens on September of 2015, this was observed for the first time. And let me see if I can let's hope that the sound is working. So there's it's in some sense a telescope, but it's, this is a bit of an aside, but I think it's really cool, called LIGO, the Laser Interferometer Gravitational Wave Observatory. And it's in some ways like a microphone that's listening to gravitational waves. And this is what they heard. Just a little blip. So that's been converted to audio so that we can actually hear it. But what they saw was these signal of ripples in space-time making a noise in their telescope. And we can see then that there are these black holes, these pairs of black holes that eventually, occasionally merge together. And we've seen several of them since. And that actually won these three gentlemen the Nobel Prize. But, which is another great discovery, and the product of something like 40 years of work to try to see this thing. But now there's an astronomical question. So now that we've shown that these gravitational waves exist, we wonder where did all these black holes come from? So that's another question that we probably have the answer for when we can understand the cosmic dawn. And then lastly, there's this period I was talking about, the epoch of reionization, which we think looked something like this. So as the first stars and galaxies started to turn on, they're shooting out all kinds of light, not just visible light, but ultraviolet light and X-ray light. The kind of light that the ultraviolet, for example, gives you a sunburn. It's basically the same idea. It's ionizing radiation that goes out to the gases and galaxies, and it starts to turn it from neutral to ionized again, hence the name, the epoch of reionization. So, the cosmic dawn, despite being a process that happens over about 1 billion years, roughly speaking, though we don't know exactly how long it took, that does sound like a relatively small fraction of the age of the universe, and that's true. But there's another way of looking at this that I think is in some ways more elucidating, and it has to do with the expansion. So let's imagine that this is our observable universe. So we can look out in any direction, and we're seeing back really far in time. We're seeing 13.8 billion years into the past when we look at the cosmic microwave background. But we're also just looking at a thin spherical shell. So I'm not claiming that this is the whole universe. I'm just saying this is the part we can observe because we can't observe any more distant than this. And we can observe roughly the same distance in all directions. So the universe, the observable universe, looks like a sphere. So the cosmic microwave background is just this thin shell, this thin outer shell of that sphere. And that galaxies that I showed you, that flyby through the Sloan Digital Sky Survey galaxies, are actually a tiny fraction of the volume. This is to scale of the entire universe. So from here light has come, basically the universe has expanded by a factor of 2 since light came here. From here the universe has expanded by a factor of about 1,000. And because of the expansion of the universe, it actually means that it's a relatively small volume today that accounts for a large amount of the cosmic time. That's a bit tricky, and I'd be happy to explain that again. And I think probably you have to hear it like 10 times before it starts to make sense. The expansion of the universe is a little mind-blowing, and that's okay. But the cosmic dawn, this period that we're interested in, actually constitutes the majority of the volume of the observable universe. So it's no small thing that we're going after. It's actually a huge part of what we can ever possibly observe. Because there's nothing, by definition, outside the observable universe, there's nothing to observe. So we're really going after a big fraction of what's out there, and sort of as explorers, that seems like a logical thing to go after. Any questions before I go on? Yeah?
Yeah, is the expansion of the universe consistent all over? In other words, are there parts of the universe that are going a little faster, a little slower?
On relatively big scales, it seems to be consistent. If you go further back in time, which means further away, there's different speeds of expansion, and that has to do with the dynamics of dark energy and dark matter. But we also think that where we are here, at that corresponding time would have been expanding at that same speed. So as far as we know, that expansion is homogeneous in the sense that it's the same everywhere, and there's no evidence to the contrary. I can't prove that it is, but it seems like that's the simplest model that fits the data. Question?
Could you explain again why this area is represented by kind of a milky film and with bright yellow in the middle? Is this like a visual representation, or
Yeah, I mean,
what it would actually look like visually?
This is an image from Scientific American. This part in the middle here, or this part here?
The part that you're working on.
Yeah, the cosmic dawn. So this is sort of to represent the idea that the first stars and galaxies were producing bubbles of ionized gas around them, and eventually those bubbles, as we move to the right here, are merging together to the point where the entire volume of gas between galaxies becomes ionized again. So it started off with just a few brightest things, the first stars and galaxies, and eventually they were enough to reionize the whole universe.
So this would not be...
It's an artist's representation, for sure.
Right, but it would not be visible to the human eye, basically.
Not as such. So the galaxies themselves, if we were close, we could see those. But the impact on the gas between galaxies, which is what I'm going to talk about in a minute, is a little harder to see with the naked eye. Hydrogen is hard to see. I don't know if anyone here has seen hydrogen.
I look at it all the time.
Yeah, right. So, let's talk about actually how do we go and measure this, and I'm going to get to this question about hydrogen in a minute. And, well, the answer is the hydrogen. So the hydrogen gas makes up the majority of the regular matter. That's still only 5% of the total mass of the universe, but it's the majority of the stuff that we can see. And, like the famous drunk who's stumbling under a lamppost looking for his keys, you look where you can see. That's the first place you look. So we can look at the hydrogen. And in particular, we use this property of protons and electrons that's called spin. So spin is a suggestive name, but don't think of the protons and electrons actually spinning on some axis. They are, to good approximation, point particles. So it doesn't quite make sense for them to spin, but they have angular momentum. This is a quantum mechanical effect, and I don't think I'm going to be able to explain it if you don't accept this idea. Let me just say that they have something called spin. And they can have spin that's aligned or anti-aligned. So, let's get that. So one thing that can happen is if the spin flips, meaning you can think of it as rotating clockwise, goes to rotating counterclockwise, so that's not quite right. You can actually change the energy state. So many of you might remember from chemistry, if you take an electron, you put it from one orbital to another orbital, you change the energy state, and maybe some light is given off. So the same idea is true here, except instead of electronic orbitals, we're talking about spin alignment, and so the energies are a lot lower. But what you get when this spin flip happens is that it produces a photon, a little bit of light. And unlike the light we see, which has wavelengths in nanometers, that's 1/billionth of a meter, we're seeing light that comes from the hydrogen that has a wavelength of 21 centimeters. That's less than a foot, but not a lot less than a foot. Which is a weird thing to think about as a particle having that long of a wavelength, but that's what a radio wave is really made of, is these photons. It's all just light. So this light is produced with a characteristic wavelength of 21 centimeters, and then it goes off in the universe somewhere. And our goal is to try to find it. So only, I should add, neutral hydrogen, which means the electron and the proton are spinning around each other, not ionized hydrogen, which means that they've been dissociated by some highly energetic process, can emit this 21 centimeters. So what we're trying to map is the neutral hydrogen, the ionized hydrogen to looking when you're observing with 21 centimeter light, looks invisible. Okay, so that's the basic idea. We're trying to make maps of this process of the ionization of the universe, which is this process that's going on during the cosmic dawn. And we can look at the neutral hydrogen, and we can make maps of what's going on in the universe, and then we don't see directly the stars and galaxies that are actually producing the ionizing light, but we're seeing their impact on the gas between the galaxies on the intergalactic medium. So we can, by measuring this 21 centimeter light, we can see the neutral part of the universe, which is, persists until basically the end of the cosmic dawn, where the whole thing becomes re-ionized again. So one question you probably would ask is, okay, we go out and measure a little bit of light, and that's not quite how radio telescopes work, but we'll get there in a sec. How do we know how far away it's it actually came from. How do we know what part of the universe it came from? So we know what direction it came from, but we can also figure out the distance it came from by the wavelength that we measure it at. So the idea is like this. So if something is from further away, that means it's older, because it took longer for the light to get to us, so we're seeing the universe as it was a little bit older, or a little bit earlier on, and therefore the light is redder because it's had longer to expand. And by redder, I mean longer wavelength, and now it's not really fair to think about blue and red, although we still use those terms, and those are terms borrowed from our actual vision, but longer wavelength, we think of this as being quote-unquote redder, and shorter wavelengths therefore correspond to younger parts of the universe. Let me say this better. It's a younger part of the universe from our perspective, not from the beginning of the universe, but we're seeing something that's nearer and therefore bluer. So it's had less time, the light has had less time to come to us, it's had less time to expand with the expansion of the universe. And so the idea then is what we call 21 centimeter tomography. Now, some of you may be familiar with tomography in the context of, for example, a CAT scan. The T in a CAT scan stands for tomography. And the idea is that you're making maps in slices. So different wavelengths correspond to different distances away from us. And so by observing in many wavelengths at many directions at once, we're making these, in theory, giant 3D maps. So that's the core idea here. So another way to think about that is that if we're looking at hydrogen that's nearer to us, its light is going to have a shorter wavelength or a higher frequency. It's going to look quote-unquote bluer. But again, these are radio wavelengths, so they're not blue or red really. And if it's from further away, if it's from closer to the beginning of the universe, it's going to look red. And so that's the basic idea, is that we're making maps of the universe in slices. And so we can think about the part of the universe that is potentially mappable with this technology as being sort of roughly from when the universe was about half the current size to when it was 50 times smaller. And beyond that, it's actually pretty hard to observe with this particular technique, because the hydrogen is just not behaving, basically. I can tell you about that more later, but that's so far away that it's pretty futuristic. So it's still a huge volume of the universe that could potentially be mapped out in 3D slices, to make a giant 3D map. And that's the basic idea. So, how do we actually go and observe this? And I'm going to show my one real equation for the whole talk, which is as follows. So we're looking for frequency of light, and 21 centimeters, so if we do, the equation for frequency is the speed of light divided by the wavelength, lambda is a wavelength, so the speed of light divided by 21 centimeters, and that's 1.4 gigahertz, or 1420 megahertz. So that's a frequency of light, and it's in a unit that people more often associate with like a radio station. So radio stations, as I'll come to, are often measured in megahertz or kilohertz. So we're talking about, if we're interested in the first stars, we think that that's maybe when the universe was about 30 times smaller. So that means that the 21 centimeter wavelength has now expanded by a factor of 30 and is now out at 6 meters, which is about 50 megahertz. To the epoch of reionization, we think ends probably somewhere where the universe was 7 times smaller, which is 1.5 meters, which is 200 megahertz. So that's the range of frequencies that we're interested in. So when the light is emitted, it comes out at 1420 megahertz, or 21 centimeters. But when we observe it, it's grown much bigger. It's grown to a few meters in wavelength, which is really like, I am roughly 2 meters tall. So this gives you a sense of how big this light has gotten, because it has been allowed to expand with the expansion of the universe. Now, some of you may look at these two frequencies, 50 to 200 megahertz, and see immediately that there's a problem. And the problem is us. The problem is humans. So you can't do this kind of observing in any place with, say, radio stations. So, for example, in San Francisco, KQED emits at 88.5. You hear KQED 88.5, that's in megahertz. So that's 3.5 meters wavelength. That means the whole time, around 270 million years after the Big Bang, that's gone. We can't see it if you're anywhere near San Francisco. Or KFOG is at 340 million years after the Big Bang. So I actually have a live demo, and this is always a little bit risky, but let's see if we can get it to work. So what we're looking at here is a little radio, and it's connected to this thing called a software-defined radio that goes right into my computer via USB. 20 bucks on Amazon, it's pretty cool. And this is what radio stations look like. So what we're seeing here is a radio station and its sidebands for the aficionados. But what we're seeing as we scroll through the different frequencies here, so let's see if I can do this with, is we can scroll through the frequencies and we can listen to, let's scroll over to NPR. So that was 88.5, so I'm going to scroll over to 88.5. There's something bright there at 88.5. I'm going to turn it on.
Of miles being driven on our roads. What we need to do to change that is that right now you
So
pull
this
your
is
app
live
and it's
radio.
just so convenient, both Lyft and
I
Uber,
can
just go with that.
Play it as it sounds if you are not demodulating, which is a fancy term for what the F in FM, sorry, the M in FM is modulation. So this is what that sounds like. Oh no. Pretty terrible. Okay, I won't torture you any longer. Yeah, so this is what the radio spectrum looks like, and it's just full of humans. It's terrible. So what we need is to go somewhere where there are many fewer humans, and our solution to that problem is to go here. So that's the Karoo Radio Observatory. If you don't recognize the geography, this is the southern tip of Africa. This is South Africa here. And we need to get far away from humans. So down here is Cape Town, up here is Johannesburg. We are far from basically everything. And we're building a radio telescope in the middle of the desert because humans are in the way in much more accessible places. And so when you go to the middle of the desert, it's not easy. It actually, it's kind of a bit of a Wild West astronomy. You really are dealing with shipping containers and laying out spools of wire and that kind of thing. This was before my time on the site, but that's now a tenured professor at the University of Pennsylvania, hammering down some stakes. And the first thing that was built on this site was a telescope called PAPER, the Precision Array for Probing the Epoch of Reionization, or a thoroughly ungoogleable acronym. And PAPER was made up of these, these are basically antennas. You can think of these as like radio antennas. These are crossed dipoles, and they're sitting above these things which are a few meters in size. And this is matched to the size of the light that we're looking for. So we're looking for light that has a wavelength of a few meters. So we don't need perfectly polished glass mirrors. It's not like optical astronomy. To us, at these wavelengths, chicken wire mesh looks like a mirror. Chicken wire mesh, because it's electrically conductive, it reflects the light. So we don't need to build the most perfect kind of optical elements. What we need is to build a lot of them. So these things are big and they're a bit heavy. And eventually, with PAPER, they built 128 of these out in the desert. And that was a good start. But the signal we're looking for from hydrogen is coming from very far away, and it's quite faint. And that's been one of the biggest problems, is that we're looking for something that is just really hard to see, because it's first from coming very far away. And even though hydrogen is so common, this is not a common process. This particular 21 centimeter bit of light doesn't happen that often for any given hydrogen atom. So we're saved by the fact that there's so many hydrogen atoms, but we need to build a big telescope. So even with 128 of these little dishes, that was not going to be enough. And we kind of knew that even from any theoretical prediction that wasn't going to be enough. So we needed to go bigger. That's usually the answer in astronomy, is just build it bigger, spend more money, and make it bigger. And so we're going way bigger, way bigger, with something we call HERA. So HERA is the Hydrogen Epoch of Reionization Array. This is obviously a drawing in AutoCAD. It's not what HERA looks like. I'll show you in a second what HERA looks like. But HERA is a collaboration, a very big collaboration now, with dozens of people across more than 10 different institutions. And I should also mention that we are funded. I skipped that. Sorry. I should also mention that we're funded by the National Science Foundation and the Gordon and Betty Moore Foundation, who have been very generous in helping us build this thing. So to give you a sense of scale, if some of you have seen the movie Contact, HERA is going to be as big as Arecibo. So this is about 300 meters across. That's 900 feet. That's how big HERA is going to be. And each of these dishes individually is 14 meters. That's 50 feet in diameter. And we want to build 350 of them. And that sounds like it would be really expensive, and it's not cheap, but it's actually not quite as expensive as you think. And I'll come to why, but basically these things are made of PVC pipe and chicken wire mesh and telephone poles. I'll show you pictures in a bit. They're quite cheap to build individually. But let me get, before I actually show you pictures of what this looks like, many of you look at this thing and probably say, well, wait a minute, is that actually a telescope? That doesn't look like any telescope I've ever seen or used, right? A lot of you actually go out and observe with real optical telescopes and are probably better at it than I am. I can like barely find, you know, Mars or whatever. But this is actually a telescope, but it's not a normal telescope. This is what's called an interferometer. So there's a few famous telescopes like this. There's ALMA, there's the VLA, and this is a technology you can do with radio telescopes, and here's the basic idea. So each of these elements, each of these antennas, and remember these are big, they're 50 feet across, are just looking up. And we let the sky rotate over us. So we're going to make a map by looking at a stripe of the sky. So we've given up on observing the whole sky, but that's okay because the universe is basically the same everywhere. So we can look wherever we want, and up is the easiest place to look. So we're looking up, and we can see a pretty big area. So we're looking at an area that's about 10 degrees across. That's the size of 400 full moons. So it's not small. It's actually quite big by astronomy standards, but it's not like it's the whole sky. Not yet, not with this generation. So each of these is just looking straight up. So they're seeing the same part of the sky. And what you do is you say, okay, I'm going to take the electrical signal, because we're not actually measuring, we're not using CCDs like a normal telescope. We're not using buckets of light. What we're thinking of is instead, the light is coming in and it's exciting electricity in the antennas themselves. And we're measuring that electricity using hardware, the same kind of hardware that's actually used in cell phones, for example. Which is another reason we have to stay away from cell phones, and you're not allowed to use cell phones on site. So these signals, we take the signals from a pair of antennas, and we send them to a supercomputer. And actually the reason that paper was called paper is that a professor who passed away a few years ago, who was the founder of that project at Berkeley, his name was Don Backer, famously said that if you want to observe the epoch of reionization, what you need is paper clips and a supercomputer. The thing on the site is not that complicated. What's complicated is the actual computing machinery that goes on behind it. So we take a pair of antennas, we send it off to a computer, and what they can see is not one particular direction, but they actually see a kind of a wave pattern on the sky. So if there's light here, or here, or here, or here, or here, they'll be sensitive to that. And if there's light in these regions where it's sort of a null, they're not sensitive to that. So you're able to measure one particular wave pattern on the sky. For the experts, that's called a Fourier mode, but I think it's good enough to know that it's just, you're measuring not a particular direction, but some combination of a few different directions. And if you take then a pair of antennas that are much further apart, what you measure is a much faster mode on the sky. So it's going up and down a lot. So we can see things here, but not here, and here, but not here, here, but not here. So we're seeing some combination of different angles on the sky. And the fact that you can actually combine those all together is pretty amazing, but you can actually combine them all together to make pictures. So one way to think about this interference pattern, which is fundamentally what we're seeing, is if you have a pair of tennis balls on the water and you're bouncing them up and down, you get these characteristic patterns, and it's the same basic idea. So we're able to see light basically coming from this direction, but not this one, and this one, but not this one, this one, but not this one, and that's with one pair. And now we take all the different pairs. So that's, for the math fans here, that's actually goes like the number of antennas squared, which is why the computation gets quite challenging. And you send it into a supercomputer, and you make a grad student sit there for a while and hook it all up. And eventually, you are able to actually make pictures of the sky. So this is what the Milky Way galaxy looks like, roughly speaking, at the frequencies we're interested in. And this is the part of the sky we're going to observe. So we're down. This is the North Pole, this is the South Pole. We're down in South Africa, we're looking straight up. So that's at minus 30 latitude, which means we're observing at minus 30 declination, for those of you who are, for the amateur astronomers, which is a number of you. And we use that then to make images of the sky. So just to give you a sense of what these things are like, I actually got to go there, which was really cool. And you can see that these things are not actually that expensive as individual elements. They look big, they are big, they're huge, but they're quite cheap. They're only several $1,000s each one, which is good by professional astronomy standards. And you can tell as you get closer, like, this is chicken wire mesh, this is PVC pipe, these is just like 2x4s, these are telephone poles that we're putting out in the desert. And we can build something that's really big. So we're making a lot of progress on the ground using local construction teams who are going out there in the desert every day and building, putting in poles and building these, building each of these dishes. Each one is built basically by hand. You can't prefabricate it, you build it right there on the site. And right now it's under construction. We're continuing to expand out as we try to get to our goal of 350 elements. So there's local crews, we have engineers from South Africa, we send out graduate students, we send out postdocs who are less useful and faculty who are even less useful on the ground. And we're making a lot of progress. So this is what the entire core is going to be. That's that whole Arecibo-sized circle on the ground, which is exactly where paper, the predecessor, used to be in this circle here. And here's another radio telescope called Meerkat on the same site. And it's also just really pretty. So I like to take pictures, and I got to take some really nice pictures on site. We happened to have a day with just some really beautiful clouds, which for radio astronomers is fine, for optical astronomers not so much. And I got to see a gorgeous sunset. So that was pretty cool as well. So it's out in the middle of nowhere, it's very remote, but it is a beautiful place too. So, as I have alluded to, and actually this is a good point to ask if there are any more questions before I go on.
Is the geometry of these things such that they only pick up the light that you want to see, or they pick up every?
So, like the parabolic?
Yeah, and the size of it?
Yeah, so it's a trade-off. Bigger means that you have more observing, but bigger means that each individual element is more expensive. So there's a cost-benefit analysis. But basically what's going on is that this is a parabola here, roughly, and light comes in from the top, and it bounces, and we're trying to direct it to the focus, which is an antenna up here. And this is actually basically a paper antenna hung upside down over a big dish. And that's the basic idea behind HERA. So it turns out the dishes have a number of nice features, and we're just building lots and lots of dishes on the ground.
Is the computer differentiating the light that you want to see, or is the shape of the dish?
So the dish gives us sort of light that comes from a relatively narrow region straight up. But actually to figure out, and I'm going to get to this in a minute, to distinguish between what we want to see and what we don't want to see is a much thornier problem. So for the most part, we're just looking straight up. Occasionally, there are bright sources like satellites and airplanes that go overhead. And then, of course, there's a few radio stations that are like way far away, but still quite bright by our standards. Not nearly as bad as if we tried to build this thing in the Bay Area, of course. But one of the biggest challenges, yeah.
What is the accuracy of the construction of these?
That's a great question. So they're trying to get things to be accurate to a few centimeters, although with those panels, it's quite hard. So it's probably order 10 centimeter accuracy. But we're looking at light that has wavelengths of several meters. So it doesn't have to be that accurate. And we also have to think about how sort of the differences between antennas. This is getting into a paper that I literally just published a few weeks ago about how those differences with antennas actually affect our analysis. It gets subtle, but in general, they don't have to be that perfect. Yeah?
What kind of weather is there in that area, like sandstorms and things like that, and how are these designed to resist it?
Not much in terms of sandstorms. There is a fair bit of wind. So this is Kevlar cable under pretty high tension. And so that keeps things more or less stable. There's lightning occasionally on the site, so there's some lightning rods as well to avoid frying the electronics from the lightning. And it rains occasionally, so there's like drainage ditches that go through there. It's technically a semi-desert, according to Wikipedia, not an actual desert, which I only found out when I went there. I don't know exactly what the definition is. I'm not a meteorologist. But yeah, it's not that bad in terms, it also does get fairly hot in the summer. So we have to make sure that the electronics are in these air-conditioned huts, basically, so that they don't fry. But the stuff that's hanging, the electronics that are in here are built to withstand, over 100 degrees Fahrenheit. So, another thing that makes this measurement hard is that, well, in theory, what we're measuring is this 21 centimeter signal that comes from the early universe, this cosmological signal that we're interested in, which, we're looking at basically the parts of this that are not ionized yet, and we're watching the evolution of that. In practice, as I mentioned, that signal is really, really faint. And sitting in front of it is everything else. Our galaxy, other galaxies, and they're all emitting radio waves too. And so that makes it sound like kind of an impossible problem, because the foregrounds, which everyone else is just like the rest of the universe, is 100,000 times brighter than the signal we're looking for, roughly speaking. We don't know exactly how bright it is because we haven't seen it yet, but theoretically speaking, it's about 100,000 times brighter than we're looking for. So that raises an obvious question. Our galaxy and other galaxies are everywhere, and there's nowhere we can look and see beyond them. So we can't pick them out by looking at a particular place. So we need another strategy. And the basic idea is to use the spectrum, the light that comes from the early universe. So as we are looking at light that's coming to us from some part of the universe, because we're doing tomography, we're looking at it in slices. And each slice corresponds to a different wavelength, and therefore a different frequency. So if we make a map of the 21 centimeter, if we make a graph, rather, of the 21 centimeter figure, we're looking at different frequencies, we're looking at different parts of the universe. So some parts of the universe are ionized, other parts are neutral, and as we go through and look at different frequencies, we're looking at different parts of the universe, and they're more or less separate in terms of what's actually going on there. They're looking at almost completely different, disconnected parts of the universe that are order millions of light years apart at each different frequency we're observing. And as that signal comes to us, we see that as a very complicated signal as a function of frequency. So we're looking at different frequencies, which again lower frequencies correspond to more expanded light, which means older parts of the universe. And the light that comes from our galaxy and other galaxies is produced by a totally different process. While it's at the same frequencies we're observing, it wasn't emitted exactly at 21 centimeters. It was emitted by a process that produces very smooth frequency light. And so if we know, for example, what's going on at one frequency, we can very strongly predict what was going on at another one. And that's the key to separating these two things. So the way I like to think about it is with this as a metaphor. So people have probably seen these equalizers, and this is a spectrum analyzer. And what we're seeing is, in audio, really frequency and amplitude. And it actually says here, these numbers are in hertz. And in audio, we're looking at 30 to 16 kilohertz, which is different from the numbers we're thinking about. But again, frequency versus amplitude. So this is the bass, and this is the treble. And what we're really seeing is that the bass is dominated by the foregrounds, our galaxy, other galaxies. And the treble is the cosmological signal. And now it kind of gives us an idea of how we can think about separating the two, which is we want to basically do a filter, like we have filters on audio equipment, where we say, oh, I want to turn down the bass and turn up the treble. And I wish it were that easy that I could just turn some dials. It's not quite that easy. But that's the basic idea. So what we need is basically clever algorithms and statistics to parse this out, and I'm going to give you kind of a metaphor for that. So let's imagine that the cosmological signal was this song. Let's see it play. Nope. Let's go back. Cosmological signal. Aww. Audio has died.
Oh, no, I can do it.
Okay. My metaphor is not working so well.
Could you sing it?
Sorry.
Yeah, no.
That's why I turned it.
That's why.
Yeah.
Okay, hold on. Let's get rid of this guy.
Yeah.
Okay. One more try. Everything was going so smoothly. Okay. This is our So that's the metaphor I want to use. And yes, I chose that song on purpose. It's too obvious. And so we can think of that if we just plot the spectrum, is we could say, okay, just like the cosmological signal, it's kind of complicated and there's signal on a lot of different scales. So this is the bass, the treble, and this is the bass. It's the low frequency, the high frequency, and we just plot the power on different frequencies, which is the loudness on different frequencies, we get a plot that kind of looks like this. And the noise makes it look like this. There's always noise in our measurements because we're just dealing with electronics, and that's how things are. So when we measure, we have to deal with the fact that there's noise that is just adding random stuff to our measurements. So we have to measure over and over and over to average out that noise, and that's why we need these giant telescopes which have lower noise. So we also have the foregrounds to deal with, and that's the base. And it's way brighter than everything else. So in there, though you can't hear it, was still the same song. The Across the Universe was still in there, it was just totally drowned out by the base, which is, in this metaphor, the foregrounds. So what we could do is basically try to throw out the foregrounds and throw out the noise. It gets like this. Which is definitely recognizable as the song, though not as good as the original. And actually, part of my PhD project as a graduate student was thinking about, okay, let's not just throw out all the bad stuff, but let's try to weight things in a way that preserves as much information as we can. And that was this base I found. So just with some clever statistics, we can actually recover more of the cosmological signal that we're looking for, and still deal with the fact that there are these overwhelmingly bright foregrounds that we filtered out. So, we still haven't seen the signal because we're still building this telescope because our previous generations were bright enough. But we think within the next few years we should have the raw sensitivity, the collecting area, to actually see it and to start making these 3D maps. So we're going to finish by the end of next year 350 dishes. So we're out in the desert now building, as maybe not literally as we speak, but more or less as we speak. We're continuing to build out our telescope. And we've already been observing with about 50 of these antennas. And the nice thing about using an interferometer is that an interferometer, even if you have not the full thing, if you haven't built all the antennas, it's still an interferometer. You can still combine pairs of antennas and measure these different modes on the sky. And there we go. We're hoping that we'll make this sort of first detection of the fluctuations of this map of the epoch of reionization and the cosmic dawn using 21 centimeter, and we'll be able to see further than we're able to see with most other kinds of light. And eventually, though this is still relatively futuristic, we'd like to make these giant 3D maps of the majority of the volume of the universe. So HERA doesn't even see the whole universe, it just sees a stripe. And it's going to be difficult to make maps that are not thoroughly contaminated by noise and whatnot, but we should be able to do at least some mapping. And as we continue to build this technology and build bigger telescopes and be able to analyze the data better, we should actually be able to make these giant 3D maps of the universe, which will be the biggest maps we've ever seen. Now, I normally would conclude there, but there's been an interesting wrinkle in the last few months in this field, which I will just touch on with one slide before I conclude. So there's another way of going after the signal. Instead of building these giant telescopes and looking for trying to map out the signal as it fluctuates, instead, one thing you could do is just try to measure the average signal over the whole sky. So that's a harder measurement in many ways, because it's much harder to analyze the data and much harder to calibrate, but you don't need nearly as big of a thing. This is just a couple meters. This is a single dipole, a single antenna that's out in the middle of the desert in Western Australia, and they're claiming to see the first signature of this cosmic dawn signal from 21 centimeter, and they actually published in Nature a few months ago. But what they're seeing is really weird. They're seeing a signal that is something like twice as large as what anyone would have predicted ahead of time. No one thought that they would see anything, but it was still good work. They were supposed to just set limits on how strong the signal could be, and yet they saw something. So what that something is a good question. One thing it could be is it could tell us something about dark matter. It could be that the universe was too cold at the time that they were observing, and if it's too cold, the only thing colder than the gas between galaxies is the dark matter, which means that somehow the dark matter and the gas had to talk to each other in a way that we don't think that they can, and one cooled the other. So that's one potential explanation. Another potential explanation is that they're wrong, and what they're seeing is just foregrounds and their electronics in some weird combination, and it's really hard to tell the difference. But with HERA, because we're measuring so many more things, we're making these much more detailed measurements, we're able to check ourselves with more self-consistency, and so we should be able to follow this up. So if it's real, we'll see it. And if it's much brighter than anyone predicted, we'll definitely see it. But also it might not be real at all, and that's just how science goes. And so we're going to follow it up experimentally, and we're going to find out whether this is right or not. But either way, even if they're wrong, we should still see something. And we should be able to start learning about our cosmic body. So with that, I want to conclude and thank everybody for coming, and I'm happy to answer questions. Before I do that, I do want to do a quick advertisement for a project I'm involved in called the Science Ambassador Scholarship, which is a full-ride scholarship for college for women who are studying STEM fields. And the video applications are actually, so you do a 3-minute video lecture on any topic, and you put that on YouTube and you submit it, and you could win a full-ride scholarship to college. And you can go to scienceambassadorscholarship.org, and the video applications are due December 11th. So not that long from now, and I just wanted to put that out there. If there are any women who are going to go to college in the next year, or who are currently freshmen in college and looking to get some money to continue to study in STEM, or people who know women who are about to apply to college. So with that, thank you very much. And we've gone a bit over time, so if people need to leave, feel free, but I'd be happy to stick around and answer questions. Yeah?
When you have all the 350 antennas, what would be the resolution in the sky, like in arc minutes or whatever?
That's a great question. So for those of you who couldn't hear in the back, the question was what was the resolution that we're seeing in terms of arc minutes? And it's actually, the answer is it's a few arc minutes. So it's actually not very high resolution. And I'm going to throw out another equation, which is that the resolution of a telescope is just, roughly speaking, about lambda over d. So that's wavelength over diameter. Is roughly speaking the resolution of a telescope. That's the angular size in radians or degrees that you can see. And so because we're looking at such long wavelengths, we're talking about 2, 3, 4 meter wavelengths, our resolution is not that big. Even though we have diameters, the way that interferometer works, you can think of it as the diameter of the whole thing, which is several hundred meters, which is much bigger than any optical telescope out there. We're looking at such long wavelengths that we don't actually have that fine resolution. So to start with, we may make these 3D maps of the universe, but they're not going to be the prettiest maps ever made. They're not going to look like the Sloan Digital Sky Survey, not yet. But the volume of the universe that's accessible, because we have this big, relatively big field of view, even though we have big, fat pixels, we can still see an interesting structure. Question?
Yeah, are there other natural sources of radio emissions that are other than 21 centimeter redshifted?
Right, so the question for the people in the back was whether there were other sources of radio emission. And the answer is there's quite a few. So the foregrounds that I was talking about, our galaxy and other galaxy, those are not emitting 21 centimeter light. So those are from the nearby universe, so that light has not been redshifted. And so when it's emitting at the frequency more or less that we're observing it. So that's 150, 200 megahertz, something like that. So that comes from a process called synchrotron radiation. There's also Bremsstrahlung, which is a mouthful of a German word for another kind of radio waves that are produced in the universe. There's lots of different ways to produce radio waves. And most radio astronomy is done with other things besides this 21 centimeter line. This particular frequency that comes from hydrogen. There's lots of other things that emit radio waves, but for us, the dominant thing is the synchrotron that's in the way, but it's very spectrally smooth because it is produced by a totally different process, a process that has not one characteristic energy or frequency scale, but has this broad distribution. And it's that broad distribution that actually ultimately saves us. Over there.
Yes, that nature paper of the edges, like what range of redshift, how did they know what redshifts they were looking at?
Right, so they know what frequency they're looking at. So, sorry, the question was how does edges, this little guy in the desert, which is, it's pretty cool if it's right, because it's an experiment with a team of like 5 people at MIT and the University of Arizona State. Sorry, shouldn't make that mistake. How do they know what redshift or age of the universe they're looking at? So this particular antenna observes from 50 to 100 megahertz, which is a wavelength of 6 meters to 3 meters roughly. So that's the range they're looking at, and the signal that they saw was at about 78 megahertz, I want to say, which corresponds to a redshift, which is an expansion factor of the universe of about 17. So the universe was 17 times smaller.
So they saw excess emission at that particular.
So the question was if they saw excess emission at that frequency. Actually, they saw absorption, which is real weird. What they saw with the light was actually, so this, I didn't mention this, but the 21 centimeter light that is emitted by hydrogen can also be absorbed by hydrogen, because any kind of atoms, when they emit light, they can also absorb light and do sort of the time reverse process. So the spins flip one way, they absorb light, they flip the other way, they emit the light. So we're mostly interested in emission, but if it's an absorption, that's the signal that the universe was too cold. Or rather, the gas between galaxies, the hydrogen was colder than it should have been, just from the fact that the universe is expanding, and as things expand, they just cool down. And that too cold was not predicted, and maybe what they're seeing is real, and maybe what they're seeing is not, and we have to go out and check. The question?
It's too cold by a factor of 2, which was unexpected, as you said, but they're proposing that the only thing colder than the gas, which is already cool, is dark matter.
Right.
And that would cool it even. Dark matter by default is much cooler.
Right.
And that would be what they're observing.
That's
for. And how does your paper throw light on that question?
Right. Okay. So the question was, so it was reiterating the idea that if the way that you could get this anomalously cold signal is if the dark matter, which is the majority of matter, although not the majority of the total mass of the universe, which is a bit funny, but there's a lot more dark matter than there is regular matter, hydrogen, helium, and the stuff we're made of. And if those two things could interact, because the dark matter is colder than the gas, the dark matter could take some, if they were interacting, that would allow it to take some energy away. But as far as we know, dark matter and regular matter don't interact via light. They only interact gravitationally, which doesn't let them cool each other off. So if dark matter interacts with regular matter, that would be extremely exciting. It would be a fundamental discovery about the nature of dark matter. But it's a bold claim, and it needs more evidence than what this one experiment can do. So they're right. They sat on their results for more than a year before they published it, trying to verify it and check all the things that could be wrong. And they eventually published it. And I hope that they're right, but we all have to take a skeptical approach to this, and we try to verify it experimentally. So the second part of the question was, how will HERA, our telescope, be able to go observe this? And let me go back to a picture of HERA. Yeah, we'll go with this one. So this telescope, this antenna here, was a holdover from paper. We actually literally took the old hardware for paper and hung it upside down over the new dishes. And paper could observe from 100 to 200 megahertz. But I said that the edges signal was at about 80 megahertz, 78 megahertz, I believe. So it was too low for us to see with the observing we've done so far. But on the ground right now, as we're sort of gearing up for the next observing season, we are replacing all of these, and also a lot of the computers as well, with new kinds of antennas that have a broader bandwidth. So the new antennas should be able to observe from about 50 megahertz to 250 megahertz. So that's a much wider range of frequencies that we're able to see, and we just literally take the same dishes and hang new antennas that have the ability to see in this wider bandwidth on top of them. And we're building them out now. I don't actually have a picture on hand, but they're very funny looking. They look a little dangerous. They look like giant blades almost, and I don't want to be caught under one. But with that new set of antennas, we should be able to not just observe the universe at a wider range of ages or redshifts or frequencies, but we should be able to directly go after and confirm or disprove the edges result. And actually, we recently got another round of funding from the National Science Foundation, in part on our promise to go after the signal and either confirm it or disprove it. Which was good timing for us. Question?
I think you maybe have been explaining, and I'm not quite understanding through your conversation about filtering the signal. But my question pertains to, if I'm looking at the screen and I'm seeing that orange or red color on there, and then light that's come from a lot further away that was once blue and has redshifted and is now arriving at the same color.
Mm-hmm.
I'm not clear on how you're able to differentiate that.
Right. So for people in the back, the question was, if we're looking at, say, this part of the screen that's orange, how do you know that that wasn't actually, so how do you know that that was blue that became orange and just redshifted versus orange as it is right now?
Yeah.
And the answer is, if we're looking at just a single plane, a single frequency, we can't. We're saved by this observation, which is that we're not just looking at one frequency. My animations go a little slow when I have to. We're looking at many different frequencies at the same time. So while we can't figure out just one precise frequency, what we can do is take our maps and filter them. So they're a little different from what's actually there, but they still contain most of the information, which we can then use to test our theories about how the cosmic dawn actually happened. So filtering, if we throw away the very frequency smooth modes, or if you prefer the metaphor, if we're throwing away the bass, if you throw away the bass from a song, it's a different song. But if we understand how that happened, and we can still go and check which song it was. If I'm going to take this metaphor maybe slightly too far, it still sounds a lot like the song. It's just a little bit different. So we're throwing away part of the information because it is kind of hopelessly contaminated to save the rest. So we're not, baby in bathwater is probably not the greatest metaphor, but the point is that while we can't distinguish by looking at just one color of light, one frequency, one wavelength, it's by looking at this full spectrum that we can distinguish the two. And we're enabled by technology that underlies things like computers and cell phones. So the fact that we can take the electronic signal that's coming off these antennas and turn it into bits, we can digitize. There's these analog digital converters, which are things that were pioneered in vastly different technological domains, are extremely useful to us because we can literally take the signal and we can measure the strength of the electronic signal faster than the wavelength, faster than the frequency. For people who are familiar with digital electronics, things that are going at 250 megahertz, that's not really that fast. That's, Pentium 2 or whatever kinds of speeds, and we're much beyond that now. So we can actually use these advanced electronics that were pioneered for computers and cell phones and whatnot to do these kinds of measurements where we can measure simultaneously many different colors of light or wavelengths of radio waves.
Well then, probably in 2 more years, hopefully you're still in Berkeley, then you can come back for the follow-up in 2 years.
All right,
And
sounds
thank
great.
you so much. We
Oh,
thank
look, a
you for your
certificate.
fine talk. We enjoyed it very, very much.
Thank you.